Hey everybody, this is Taylor Sparks from the University of Utah in the Material Science and Engineering Department. Today we're going to talk about variational autoencoders. If you haven't seen our previous video from Ryan Murdoch on GANs, Generative Adversarial Networks, check it out. It was good. He's working at Adobe and does some really cool work. Today though, we're going to talk about the other popular machine learning architecture for generative models, and that's variational autoencoders, right? Before we do that, we first need to describe what an autoencoder is before we talk about variational autoencoders. What's an autoencoder? Well, an autoencoder is a way to efficiently encode data. So encodings or embeddings, right? We learned about when we talked about, say, with TSNE and UMAP clustering, we learned that you took something that was in high dimensional space, like say two-dimensional. Now in this case, they happen to be clustered. Let's ignore the clustering for a moment, but it was two-dimensional. We flattened that down to a single dimension. In the case of TSNE and UMAP, we tried to preserve the clustering. That was the whole point. But just the fact that we were flattening it down to a lower dimension, whether through PCA, TSNE, UMAP, right, that's an embedding technique. If we went back to what we had in the beginning, right, if you could not only reduce its dimensionality, but then increase its dimensionality back to the original without any loss, you would have an encoder, right? So that's what an encoder does. An encoder takes an input with some larger dimensionality, so the feature space is larger. It reduces that down, and it can do that in various different ways with fully connected layers, with convolutional layers, with different things. But then once it's down in this reduced dimensionality, sometimes called the bottleneck, like you're going to squeeze this ship down to a bottleneck, and then you're going to increase it back up, right? You're going to try and increase it through the decoder to the output, which is the same as the input. The point being that you encode information in this first part, you decode it over here, and the middle part would be the code or the bottleneck. Okay, so I think that sort of makes sense. The question is like, why do you want to do this? Well, first off, this is what it might look like, right? Let's say you have an image of a cat, of course, because it's machine learning. We love cats, right? Our encoder network might include convolutional steps, right? So we're going to do convolutions to now get what we call the latent vector, right? So this bottleneck or code region sometimes gets called the latent vector or variables, right? Which is now reduced dimensionality. And then we're going to decode this back up to try and get our original image back, right? So those are the two important steps that are present in an autoencoder. Why would you want to do this? One idea is that you might want to do it for image compression, right? There's lots of different image compression algorithms, right? JPEG, GIF, all these different things, ping. They all compress an image so they're smaller. They're way smaller than just like storing every single pixel with its information. So for example, if you have let's say you're encoding, your compression takes advantage of like straight lines and it says, oh, you've got 5 black pixels in a row. So instead of putting 0, 0, 0, 0, 0, it just says 5 zeros in a row. So it's a way to make it more efficiently compressed. And then when you're done, when you want to uncompress that, you just read back that there was 5 zeros. And there's other algorithms. I'm giving, there's a lot more to image compression, but that's the idea. Well, if you compare this new type of image compression where you use an autoencoder, they call this neural image compression, it actually has some advantages. This is from a Google blog, ai.google blog. You see that they're comparing neural networks with other approaches. So on the left, they have this picture of this supremely ugly dog, right? And in the center, they do JPEG compression, and on the right, they do a residual GRU, right? So neural compression, right? And then they zoom in, and they're talking about the advantages that it looks like neural networks have, right? They say while today's commonly used codecs perform well, our work shows that using neural networks to compress image results in a compression scheme with higher quality and smaller file size. So pretty cool. Why should you care about this? I think you should care about this because our phones are increasingly, we take all our pictures here, and then you want to be able to access your picture, but you only have so much memory on these things. So what would be great is if you could store the image on the cloud with whatever resolution or size it needs to be for permanent storage, but then when you want to show it on your phone, you could just have the auto encoder, right? You could encode it from the cloud to a smaller size, really reduce the size of this thing by sending it into the latent space, which is smaller memory. Send that over the band, over the wireless band, the spectrum, which is going to be important to reduce the amount of information that we're actually sending over the spectrum as we all compete for this limited resource. And then you use a decoder on your phone to decode that and turn it back into your full-size image right here after receiving a much smaller file size. That's just one example of the really cool things that we might start doing with autoencoders, right? So that's an autoencoder. It takes something larger dimension, squeezes it down to a code, a smaller one, a latent vector, and then it decodes that back out to your original one. And there will be some loss, but we try and minimize that loss. So we can do other things with these, right? You can do denoising. For example, let's say you have like your MNIST data set. This was like the original. Then you add a bunch of noise to it, right? Maybe it got damaged, and so you scanned it in, and now it's all noisy, right? If you've tried to read handwriting from like the 1800s, this is a real issue. So how do you denoise it? Well, you can train off of these things, and then when you receive something noisy, it can learn that, hey, those white things are not in my original data set, so I can learn to ignore those things, that noise, and just now produce this denoised image. Pretty cool. Same thing with these images where you do what's called neural inpainting, where you take an image and you're going to now delete part of it. Let's say you want to like scrub out these people in this image, and then you want the autoencoder to now, having empty space there, fill it in with what ought to be there, and it does a pretty good job. It looks like those people are just gone. Same thing over here. They cut out part of this arch, and it was able to draw it in so it looks like the rock did that on its own. Or here they had a watermark from Jiahui or whatever, right? You got rid of that, and then you had it neural inpaint with what it thinks it should fill it in. Really, really cool things happening. I remember the first time 10 years ago probably that I used content aware delete in Photoshop, where you could like circle something and just hit delete, and rather than just like deleting the pixels out and leaving an empty spot, it would fill it in intelligently. Pretty amazing stuff that we can do with these generative algorithms, right? But still, you might say like, okay, this isn't really generative. I mean, it's kind of is, but it's not like generating like a whole new picture of a dog on a trampoline or something like that, right? How do you get to that point? Well, to do that, we can't just use an autoencoder architecture. We need to do a variational autoencoder, right? So the architecture looks very similar, right? You still have an incoming image. You still have an outcoming image. You have your encoder network and your decoder network. You have your code region, right, with your latent vector. But this time, look what they've done. They've split it up into a mean vector. So your latent vector now has an average, and it has another vector representing the standard deviation, right? Two vectors. And then you have this sampled latent vector. When you put those things together, you get this sampled latent vector, and that's what gets decoded. So why? Why do this? Okay. To answer that, well, first off, let's compare their loss function is also a little bit different, right? So the loss function does get modified a little bit. In a regular autoencoder, you're just comparing the input and the output. So pixel by pixel, you could compare these things and be like, oh, they're not quite the same. They're pretty close, right? That's your first one. So this one looks pretty similar. The loss function shown here is almost the same. Scooch that a little out of the way. It's a little bit different, though. The first term, this is your reconstruction loss. It's the same as the autoencoder. That one's here. Except that now you have this expectation operator because you are sampling from a distribution. More on that in just a minute. What is this sampling from a distribution business? More on that in a second. But this second term now says this is your KL divergence. This makes sure that the distribution that you are learning is not too dissimilar from a normal distribution. So what is all this talk of distributions, right? What it's forcing you to do is that your new distribution, it forces it to have a mean of 0 and a standard deviation of 1. What are these distributions that we're talking about? Let's show you. Well, when you have your latent space, when you've encoded it down to a small space, you can now look at this latent space. Let's say you flatten it down to 2 dimensions. Then you could actually say for like the MNIST data set, right? Those are the numbers from 0 to 9 that we've been talking about all semester. Here's all 10 of those sort of clusters. And because this is a continuous latent space, you can actually move from one cluster to the other and see how the output would respond. I'll show you that in the next slide. But the point here is that you needed to learn that, you know, all of these ones over here are all 6s. 6s sort of belong in one portion of our latent space, whereas 5s belong right here in a different portion of our latent space. The way that we learn that is by thinking about these in terms of distributions. Now, if you just pulled from a random, say, normal distribution, then you have the problem that we can't undo that in backpropagation. And yet, because this is a neural network, we need to be able to backpropagate all the way through back to the beginning. And we wouldn't be able to fix that. And thus, they came up with the so-called reparameterization trick, which was so clever. The vector had to account for a normal distribution, that's epsilon. But the way that they were able to leave that constant is by saying, well, let's just say that it's a normal distribution multiplied by some tunable parameter sigma, and adding to that some tunable parameter mu. So now you have an offset and a multiply scaling one, which allows us to scale and offset from our original normal distribution. Pretty clever. So mu and epsilon become tunable parameters, right? That they get tuned during backpropagation. but we're still pulling from a distribution. So the whole point here is that you're trying to say, all right, every time that I've seen a 7, I'm going to learn where to put it so that it sort of maps it onto a normal distribution that has a mean of 0 and a standard deviation of 1. That's really important. It's learning where to put all the things that are similar to one another in a place so that then when we want to sample from this place, we can pick a number from that region and say, this is a newly generated 7, right? That's what this can do for us. Now I said that this is continuous. This space is continuous. First off, if you just gave it the latent vector random numbers, it wouldn't create anything that looks like a dog or a cat or a new material or anything. It would just create random noise. So we needed to tell it roughly the area where realistic things exist by doing it with a distribution, right? So, and if you've done it correctly, then this latent space is continuous. You can see how when you systematically alter a vector, how it changes the output image. So for example, up here you see that this version of the latent vector outputs a 9, right? So that must be right in the 9 region. But as you smoothly change this, it turns into a 6 and then a 0. As you move it down, it's sort of like a 4, and then it turns to a 7 and then a 1. You can see 8s and 3s and 2s. And it's this really cool continuous space where all of your numbers can flow from one to the other, which is going to allow us to then pull vectors out of here and say, for a new vector, which I plucked out of this continuous distribution, I can now see what it correlates to in some generated new thing. So that's pretty rad, right? Now, as cool as these are, these variational autoencoders, they can be better, right? So for example, there is something called a disentangled autoencoder. This really just changes in one significant way. The loss function looks almost the same, except now there's this beta parameter in front of our second term. The second term, remember, second term is all about making sure that when you encode something into a space that it does it in so that the mean is about 0 and the standard deviation is 1, meaning it puts it in the right distribution, right? So by adding this beta parameter, it's changing how much we scale the divergence present in the loss function. And what's slick about this is that, just like all machine learning models, beta now allows us to have that trade-off between variance and bias. So if beta is too small, you might get overfitting. If beta is too large, then you can get poor performance. So high variance versus high bias, which is kind of slick. Practically speaking, what beta or disentangled autoencoder does, it basically says, like, you start out with something in high dimensions, you flattened it down to low dimensions. What they're trying to do is making sure that each node or each feature, right, each variable in this small dimension space is as unique as possible from one another. They're not correlated with one another. Therefore, they're disentangled. They're different from one another. Here's an example. On the right, you see an entangled variational autoencoder. On the left, it's a disentangled variational autoencoder. On the right, you see that it has, like 10 different latent vectors it can use, and it's using all of them. Here's just showing you how it's using them. Like, they're all used to, when you uncode it, it's paying attention to all 10 of those. But if you introduce a penalty, right, through that beta parameter, for using more of these things, basically you penalize it. The more it uses, the more its loss function gets penalized. Then it will learn to pay attention to fewer of them. Like here, it's only using 5 of them. The other ones are all just at the mean. Like, they're just not using them. So it's forcing you to further compress it, and in meaningful ways. Like when you start using variational autoencoders, especially disentangled ones, to now generate images, and then you change one of those features in the latent vector. So one of those, say 5 features or 10 features, whatever. If you change one of them systematically, look what it does. They found that just one of them is responsible for, say, skin color. One of them is responsible for age and gender, whereas you're changing it, you're seeing these things systematically change from male to female, or old to young, or, white to dark, or image saturation. So it gives you really cool interpretability and, control that you didn't have with a more nebulous and hard, more black boxy version of a variational autoencoder. A disentangled one is much more interpretable, which is pretty slick, and they're just better, right? So let's compare our GANs, which we talked about in a previous video, with our variational autoencoders, because there's some similarities to similarities. So similarities, they both have 2 components. A GAN has a generator and a discriminator. A VAE, variational autoencoder, has an encoder followed by a decoder. A GAN plays the minimax game, where again, you're trying to make one thing perform better so that you can trick the other, and trying to tie these 2 things together, which is hard, right? Whereas a variational autoencoder simply has the reconstruction and the latent loss. So it's just a single loss parameter that you're trying to minimize based off of 2 terms, okay? The GANs are not stable, and if you've messed with them, you know how hard and finicky they can be. because you have to find the so-called Nash equilibrium, or end of game point, but we don't know what that is, right? So it becomes really hard to make these things stable. Whereas variational autoencoders have a closed form end of training solution. You're just trying to minimize your loss function. And then how good are they? Well, variational autoencoders are good in theory, but in practice, they do tend to make blurry images, whereas GANs can make really sharp images, but they tend to be a little more empirical, trial and error. Both of these tend to sample from the main part of a normal distribution, and they do a bad job of capturing the tails, right? And by the way, and there's some wild things, for example, VGANs, VAE GANs. This combines a VAE with a GAN, right? So your VAE is right here. You do an encoding down to a small latent space. You decode it to now the output, and that is the generator for your GAN, which has to have a generator and a discriminator, which is, all right, cool. And so there's many other versions of these things out there. Here's just every year there's more papers, but here's the input images. You can see what would a plain variational autoencoder do. How would a DFC, this is probably a disentangled, I don't know what that actually stands for. Here you've got the VGAN where it combines them, and then VAE GAN, that's probably a Wasserstein GAN on top of it. So all these different tools are coming out where we're getting better and better at making generative models. But fundamentally, you've got your GANs, generative, right, adversarial, and you've got your variational autoencoders. Two very different models that in some ways can work together. Okay, for our next video, check it out. It's going to be on Bayesian inference. We're probably going to split it into two. We're going to do one on naive Bayesian inference and one on Gaussian process. So stay tuned for those in our next videos.